What's going on, everybody? How we doing? I think I'm live. I have no idea if I'm actually live. Can someone chat and just say like, hey, things are good? This is very different than Zoom, folks. I can't see any of you. Okay, I see I'm live. All right, we'll give it a minute. I said it'd start at 7, so we'll go ahead and start at 7. If I were you, I would have your science notebook, your notes. I'd have your packet out, and I would have maybe something to write with, right? Hopefully hopefully you're not on your iPad only. Hopefully you've got something to write with, because we'll have two little parts to this kind of review session. So it looks like it is 7 o'clock now, so we'll get started. Here's the way this is going to work. I'm going to go through some stuff in the first half of the time we have together. Talk through some big ideas from Unit 1 in hopes that kind of refresh your brain a little bit. And then I will go ahead and field questions after that. So like your questions will be in the chat. So I'm going to go through like graphs and how we get them, what they mean, how we can use them. I'll talk through the equations, how the linearization process got us those equations, the proportionality statements that come out of those. What else? And when to use these equations. Something we already took notes on, but I'll briefly run through that. And then we'll talk about free fall and baby G. And lastly, I'm going to touch on projectile motion and the idea of simultaneous but independent motion for horizontal and vertical directions as a projectile launches through the air. So I'll cover those things kind of here in the beginning. And then if that's all you wanted was a quick review, then get on out of here. But if you've got questions on the review guide, stick around through that, and then we'll do it at the end after I'm done going over those things. The one thing, I'll talk about the questions when we're done. Okay, so obviously not in the physics classroom. I'm here in my office at my home. So hopefully we can get this thing set up a little okay, I don't have my giant whiteboards and stuff, but hopefully this is good enough for our purposes here today. So move some things around. There we go. All right. First things first, let's talk through some graphs. Hopefully you can see me. All right, there we go. Let's talk through some graphs. So the three graphs that we've talked about over the course of this entire unit, if you let me know if you can't see my board. If you have my screen big and you can't see my whiteboard, let me know. I'll try and make some adjustments. So I'll keep an eye on the chat as we go. But here we go. XT, VT, and AT graphs were the three graphs that we talked about in this unit. Okay? And what we decided was, and I asked you a couple times to translate between the graphs, to go ahead and read a VT graph, make an AT graph from there, or go ahead and read a VT graph and make a position time graph from there. So you need to be able to, or it should be expected of you, that you can go ahead and analyze these three graphs and understand how to get from one graph to the next graph. The first thing we talked about was if I was moving from my position time graph to my velocity time graph, we always said that the slope of the position and time graph, the slope of this graph gave me that graph. Okay? And we learned later that the area of the velocity and time graph bound by the function in the axes gave me the position. So the area of my VT graph gave me information about position or displacement, and the slope of my position and time graph gave me information about velocity and time. We talked about one more thing. We talked about how the slope of my velocity time graph gave me this, the acceleration time graph. So the slope of my velocity and time graph gave me information about acceleration. I'm not sure we talked explicitly about this, but I think reason would stand to say, the area of acceleration and time graph gives me information about velocity. If I take my acceleration and I multiply that by time, what I end up with is velocity. And so that's the slope, the area of my AT graph would say. So the area of this graph, the area of my acceleration and time graph gave me velocity and time. And now I gave you crazy different amounts of graphs and crazy different scenarios. Some important things to remember are like the y-intercepts and what the y-intercepts of each of these things mean. And then even the x-intercept, like what does the x-intercept mean? And again, the y-intercept would be my vertical intercept and my x-intercept is my horizontal intercept. So I'm going to go ahead and write those down below. You might want to add these to your notes as well. So for position and time graph, the y-intercept tells me initial position. And the x-intercept tells me when an object like passes zero, like when it's at a position of zero. Pretty straightforward, okay? For the velocity and time graph, the y-intercept tells me initial velocity. And the x-intercept tells me when an object is at rest. When the velocity is zero, it will cross the x-axis. That means the object has come to a rest. So it tells me when an object has a velocity equal to zero. I'm going to say 0 meters per second because typically we're dealing with meters per second. And now finally, the y-intercept of my acceleration time graph would tell me initial acceleration. And then the x-intercept would go ahead and tell me when acceleration is equal to 0. And I'm going to say meters per second squared because typically you're dealing with meters per second squared. So these are all key features that you need to be aware of when you're looking at these graphs. You need to be able to look at the slope of a graph, either position in time or velocity in time, and analyze like what's going on. You need to be able to analyze a y-intercept or an x-intercept to be able to make a statement about what is going on based on the graphs. The graphs are a way to communicate information, either to you, like from the exam or from someone to you to communicate information, or for you to communicate information back to a grader. And here is kind of the language around those graphs. Here is what the graphs mean in terms of their communication to you. That's the basic rundown of the 3 graphs that we covered. Let's go ahead and cover the equations next. I don't know this to be sure, but if I'm going too fast for you, I think you can probably pause me and then like catch up later or something like that. I think it just works like a video, but you let me know if I'm crazy and I have no idea how to use YouTube. All right, equations. The first equation, well, we have two let's break this down because we have 2 different types of motion happening in this unit. The first is constant velocity. And we talked about constant velocity for probably the first 3 days. And then we left it alone until we came back to projectile motion. Constant velocity was the dune buggy on the table on day 1. Remember when I ran past the desk and you all thought I was crazy? I said, we want to see how fast they went. I took off. We were talking constant velocity there. The dune buggy was moving at a constant speed. And so we developed an equation for that. And the equation that came out of the constant velocity was that the final position of something is equal to the initial position plus the velocity times the time. That was our constant velocity. This is an equation that will work anytime an object is moving with a constant velocity. Where did it come from? It came from our lab. It came from us graphing position and time. We graphed with an initial position of 0 because we called the beginning 0, and we saw that it moved with a constantly increasing position. This graph gave us the proportionality statement, position is proportional to time. And it gave us the equation up here because we know that y equals mx plus b. Another reason we should understand it, the slope of this graph is in fact velocity. Y equals m slope x plus b. Now you might be looking at this thinking to yourself, wait, this x related to t thing's weird. I thought we always said position was related to time squared. Like we do say that, but not for the constant velocity motion. Constant velocity motion is governed by these rules and these equations and graphs here, okay? Constant velocity means acceleration equals 0 meters per second squared. It is not accelerating. There's no outside force acting on it to accelerate or change its speed. This is the first equation we technically have for constant velocity, and the only equation we have for constant velocity. The other kind of motion that we talked about for the rest of the unit and in free fall and for the y direction for projectile motion was constant acceleration. Obviously, when it's constant acceleration, we know that the acceleration equals some number, right? It's non-zero, it equals something. So we had three equations here. And the first of those was this equation, velocity final, velocity initial, plus acceleration times time, which looks incredibly similar to the last equation we used. Why? Because it kind of came from a really similar place. In the speedier lab, when the object was going down the ramp, we saw it speeding up. But we saw it speeding up in a linear fashion. The velocity started at 0, my y-intercept, and it increased consistently as it rolled down the ramp. That gave us this line. From the line, we're able to say that velocity is proportional to time when there's constant acceleration. And then from this graph, we were able to generate y equals mx plus b. I wonder what the slope of this graph is. It's probably what's the variable multiplied by my x value. Y equals m slope x plus b. So my slope of this graph is acceleration. The slope from this equation is acceleration. When we're in constant acceleration. This is our first equation. This equation is great to use if I know information or I'm trying to find information about velocity and time. This is a fantastic equation to use if you're trying to figure out information about velocity or time, because this is the relationship between velocity and time. That's the first equation. The next equation, and one that we use really frequently, appears like this on your equation sheet. X, I believe this is x final, equals x initial plus v initial times time plus 1/2 at squared. This is how it appears on your equation sheet. That's not almost never how we write it in our class, because constant acceleration we typically talk about in the vertical direction. Typically, we write it like this. Y final equals y initial plus vit plus 1/2. We'll even do baby g t squared. And heck, sometimes we'll write it like this. Delta y equals v initial times time plus 1/2 g t squared. All of these are just different iterations of the exact same mathematical and graphical relationship. Where do these equations come from? Well, if you remember back to our speedier lab, we tried this one time. We tried to graph position in time. And when we did that, it looked like this. The position was not increasing in a linear function. So we had to use a tool called linearization. When we linearize it, we realized that this graph right here was a squared graph, which means the x variable, or time in this case, needs to be squared in order to generate a linear relationship. So we went ahead and did that. We said, let's graph t squared, or y versus t squared. And when we did, something interesting happened. We got a line. That line gave us this equation right here. It's weird to think about because there are so many variables. This doesn't look like y equals mx plus b, but it is. Check it out. if y is my y variable, nice, y equals, what's my x variable? Time squared, y equals x. So my m must be, my slope must be what's multiplied by that. So the slope of this graph is 1/2 g, or negative like 4.9 or 4.9. So y equals m x plus b. And I guess my initial velocity times time is b, my y-intercept. I don't know. It doesn't matter too much, but what does matter is knowing the slope of this line is 1/2 of the acceleration. And in instances when objects are in free fall, we can say it's negative 4.9 meters per second squared. This is the equation. This is where it came from. From this linear function, we say y, or delta y, is related to t squared for proportional reasoning efforts. This equation is great to use when I'm trying to find information about either change in y and time squared. I have that information about change in y and or time squared, or I'm trying to find one of those two. This is a great equation to use. Okay, the proportionality statement and the graph kind of hint you into when you should use it. This is the relationship between position and time in constant acceleration. That's when I should be using this equation. All right, last one. It's not one that we use often, but it is one that is super useful if we have no information about time, because this equation doesn't include time in it. I'm going to make sure I write it the way it's on our equation sheet. I believe it's written this way on the equation sheet, but in class, most often we write it this way, because in Unit 1, we discussed a lot of motion in the vertical direction. But again, both, they're kind of saying the same thing. One is just more specific, one is more general. Where did it come from? Again, the speed year lab. We graphed the velocity against position in the speed year lab. And what we saw was this kind of function. Not a squared function, certainly not an inverse function, a function that starts steep and ends shallow. If I go back to worksheet 10 in my notes, what that appears to be is a square root graph. And when we talk about linearizing or curve straightening a square root graph, instead of taking the square root of my x-axis, which is totally fine, it might be more useful for us to square the y-axis. It's the same transformation, it's the same algebraically, but it helps our equation. I don't never seen an equation with a square root sign like in it multiple times, and we would see one here. So I'm not going to do that. Rather, let's square our y-axis. When we did that, we got this linear function. The linear function, again, tells us v squared is related to y, or changing y. So when should I use this equation? I should use this equation if I'm looking for the relationship, or have information, or I want to find information around velocity and position. It's also a great equation to use if I know nothing about time. I'm not trying to find time. I don't have time. It's nowhere to be found in the problem. This equation works very, very well because it's the only one that doesn't have a time variable in it. Okay, those are the four equations we have. 3 for acceleration, for constant acceleration, 1 for constant velocity. The constant acceleration equations helped us in free fall. With free fall, we learned a few things. Free fall is vertical motion. Vertical, constant acceleration motion, in which the acceleration in the y direction is equal to baby g, which we have said all year long, or also unit long, is 9.8 meters per second squared downward. Call it negative if you want to call it negative, but you can also call it downward positive. We can get back to that later, but it is 9.8 meters per second anywhere on the planet Earth, pointed straight towards the center of the Earth. Remember, the Earth is pretty darn smooth, so we can say 9.8 for anywhere on the surface of our planet. In free fall, the change in x position is 0 meters. When we're talking free fall, we're basically just launching things straight up and letting them fall straight back down. Okay, that's really the only thing we took from there, other than a few symmetry ideas. And those symmetry ideas looked like this. If you remember right, we would launch objects straight up in the air, and they would fall straight back down. Okay, we'd say this is point A, this is point B, this is point C, point D, and point E. Here's my initial velocity. This is my final velocity. This is my top or my apex. We said one of the key ideas about this type of motion was that the velocity at the top or at the apex was always 0 meters per second. Why? Because the object has to turn around. If it's going up, it has to turn around to come back down. So in order to go from moving up to going down, in math, I think we call it the intermediate value theorem. But in physics, we say it reaches a point, its apex, it comes to a rest briefly, and then it falls back down towards the Earth. The other thing we said was that for our calculations, I'm not sure we have an explanation for this yet, other than kind of like time, maybe. We don't have a good explanation for why the velocity at point A is equal but opposite to the velocity at point E. We just know that the initial velocity equals the final velocity. They're just in opposite directions. If I launch something from A up, when it reaches the ground at point E, it's the same velocity but downward. And the same was true for B and for D. Again, B and D are points that are halfway to the apex in terms of position. So B and D also have symmetric velocities. For some reason, the velocity at B and the velocity at D match each other, but again, in opposite directions. It's almost as if point B is like the mirror image of point D. So after the object gets up to the top, it falls back to D. And because the only thing accelerating these objects is gravity, gravity has accelerated from A to B, the object, and then again from C to D. So again, there's no real good explanation for why this object mirrors or has this symmetry. We'll get a good explanation here coming up when we study energy and forces. But for now, we just were able to calculate these types of symmetries in free fall motion. Let's talk lastly about projectile motion. Projectile motion was our physics student, the one that tossed the ball through the air, and we got like 1, 2, 3 different vantage points of her doing so. Let's talk about projectiles. I'm not really going to break down the horizontal launch, the symmetric launch, and the asymmetric launch, because quite honestly, they're the same thing. Like the same physics governs them. There's just a couple different like pieces to remember, but not even really remember, right? Like if an object is launched horizontally, its initial y velocity is 0. How do you know? Because it had no initial y velocity. If an object is launched symmetrically from one spot on the ground up and then the same level on the ground, like it still follows symmetry. I still need to break my vectors apart and find my Vx and my Vy. Those things are still there. But again, it's still kind of an object in free fall vertically, moving horizontally this way. Let's see what I got to read this question here. I'm assuming this is about free fall. If 2 points like A and D have the same velocity, does the one going downwards become negative velocity? Yes, 100%. Because again, those equations include vectors, but the negative and positive are vectors. So if I'm going to have an equation where I include like the velocity at A and the velocity at D, A needs to be positive and D needs to be negative, or vice versa, but they're in opposite directions. So make sure you're plugging in the values with opposite mathematical signs. I can't plug in up and down in my calculator, so instead we use positive and negative values to indicate direction. Good question, Eva. All right, lastly, projectiles. The big idea with projectiles was the objects are moving in both X and Y directions. Now, for some reason, I was getting a lot of feedback from students on lab formatives and in class saying like the X and Y motions have nothing to do with each other. They are completely and totally independent of each other. And like, that may be my fault, but I want to break down what I said in class, because in class I said something to you. And I want to make sure you fully understand what I said in class, because it was clear to me that maybe it was a little muddy. So here's what I said to you in class. I said to you that the X and Y directions X and Y motions are, and here's where you're going to roll your eyes at me, right? You're like, Mr. Gustin, you said, but listen, right? X and Y motions are independent, right? I knew you're probably all rolling your eyes right now. Independent. And what independent means is that they're independent in terms of their position and their acceleration. Like gravity doesn't act on X like it does on Y, right? Like those things are independent from each other. The accelerations in those directions are totally independent. The follow-up to what I just said, the remainder of this statement is X and Y motions are independent. And like the most important thing I think I said about this statement was that they're simultaneous. And simultaneous literally means like same time. And I think what's interesting about same time is that it has like two meanings for us in physics, right? Like same time, meaning they happen at the same time, but like also same time, like their time is the same. Like the value we would plug in for the time variable in these equations is the same. So same time, they happen at the same time, but also like same time, right? Like plug in the same number. So when someone says to me that, I don't know, just brainstorming here, raising the height of a table only impacts motion in the Y direction for a marble rolling across the table and launching off. Like, no, it doesn't. You can't change anything in the Y direction without like somewhat changing the time the object falls for, okay? So acceleration and position in the Y direction, yes, those two things, they're independent. They occur independently because the forces in the Y direction are perpendicular to the X direction. But we'll get to that later. That's not important to us. What is important to us is that changing the time. If I change the time in either my X or my Y direction, I change it for the other direction also. I can't change time in the Y direction without changing time in the X direction. It's impossible. When the object stops falling, it hits the ground. When the object hits the ground, it also stops moving horizontally. So again, independent, yes, they are, but they're simultaneous. So the same time occurs for both the X and Y directions, which is super, super important for us to remember. And I think one of the big ideas. I guess the last thing I'll cover about projectiles is identifying vectors. I'm going to go through it real quick. And if you're still confused on vectors, I believe it's out there for worksheet number 15. 15, we break down vectors. But with projectiles, other than a horizontal launch, in a horizontal launch, we would say here, the initial velocity is equal to the X velocity. The initial Y velocity equals 0 meters per second. Right? That's kind of what makes this thing a horizontal launch. But in every other case, we launch an object at an angle, heck, let's call that angle theta. the initial velocity here is not equal to x or equal to y. But, wait, let me get more markers. More markers is always fun. Let's get some different colors going on. I got green and red. Let's see here. Should red be x or y? Okay, it'll be x. This, so VI, the initial velocity of an object launched at an angle, is not equal to either the x or y direction. Got it, cool. But I know a little bit about triangles. And because the vector is launched at an angle, and I know that x and y are naturally perpendicular to each other, did I lose the blue marker? Folks, I'm going crazy. It's too late on a Sunday for this nonsense. Here it is. Because x and y just naturally, because they're by definition make a right angle, I have a right triangle, in which the horizontal leg of this triangle is the velocity in the x direction initially, and the vertical leg is the initial velocity in the y direction. You can use any amount of trig to figure this out, but what I told you all in the past was that in order to find my initial x velocity, you're taking vi, and because it is the adjacent side, you're using the cosine function times theta. So to find your initial x velocity, there it is, vi cosine theta. And to find your initial y velocity, you're using sine theta. Vi, which is the hypotenuse, times sine, because Vy is the opposite side, theta. If you haven't yet, put your calculator in degree mode, because otherwise you're going to be converting angles into radians and plugging that in, and no one needs to mess with that. If you're not sure how to convert your calculator into radian mode, into degree mode, put it into degrees. If you're not sure how to put it into degree mode, guess what? Folks, right now, we're on YouTube. When you're done here, go YouTube how to change my calculator into degree mode. I bet you there's at least 4 videos on how to do that. So when I'm given a problem like a projectile launched at an angle, here is how I would set that up to find initial x and y velocities. One cool thing to also note, just like a side note, remember at the apex, velocity y at the top is still 0 meters per second. And we know that the velocity in the x direction doesn't change because there's no acceleration in the x direction. So at the top, y velocity is 0, but the velocity in the x direction is still equal to the velocity we had initially in the x direction. Okay? That's that. So, that's the review. If you were only here to just review some concepts and you just heard those concepts and you're like, got it, I don't know, get the heck out of here. You don't need to stay. But if you've got questions on the review, now is our time to talk about that. What I would like to talk about, green marker is barely visible. Well, then go watch worksheet 15. As we go over the review guide, here is what I don't want this session to turn into. I don't want this session to turn into, Mr. Gustin, I got the wrong answer on this problem. What's the right answer? Like, there's already an answer key posted on Canvas for you to go look at. And most of those problems have very good work associated with them, so you can go ahead and use those. What this time should be is, Mr. Gustin, I got the wrong answer. I looked at the answer key. Why is the answer key doing this? Right? Give yourself an explanation for what's going on. Or let's talk about an explanation about what's going on in the problem, as opposed to like, help, like, test is tomorrow. Let's talk about some concepts. So if you've got questions, now is the time to throw them in the chat. Otherwise, I'm done kind of generating the conversation. Now I would like you all to kind of lead it. Tenor, the answer key is on Canvas. You under the same place, in the same place keys always are. It's weird because our worksheets go like 1 to 17 or whatever. So it's actually at the top because it is an R. It's Unit 1 review instead of Unit 1 worksheet. So it's actually above all the worksheets because it starts with an R, and R comes before W. So it's there at the top. See you, Hiba. Okay. So Tanner's going to look for a question, but there are still 22 more of you here. Now we're losing people, 21 people here. Any questions? Yeah, Casey, we talked about that. Yeah. Okay, Avi. So again, we don't want this to turn into I don't understand. Like, what portion of number 37 don't you understand? What's your hang up? How did you answer the question in the first place? Like, give me some context here. Say, like, let me know what you tried, and then let me know what is confusing you about the answer key. Got it. So this is a great question because this is just what we both talked about. So Abby, that's a great example of how to elaborate on a question, right? Like, that's how you tell me where you're at. This is us trying to figure out, like construct an equation for comparing the horizontal and vertical directions. We said they are independent, yes, but simultaneous, so they have the same time. And simultaneous is giant here because we are about to look at the time it takes for an object to fall vertically compared to it moving horizontally. This is like lab formative 8 stuff, right? If you are struggling with lab formative 8, these ideas might help you answer lab formative 8. I'm gonna go ahead and grab my whiteboard so we can talk through number 37. But let's, oh, sorry, hang on. That was my scoreboard, Mrs. Guston, for our game. That's not the right side to have up. There we go. Can't erase that. She'd get mad because she's winning right now. All right, so we have an object. For those of us, this is number 37 on the review guide. There's an object. It's moving with an initial velocity of v0 or v0, and it travels off the table in this trajectory, and it travels a distance of x, and it falls a height of h. Okay, so what the problem is set up for us, the answer key set up for us is like kind of like here's the x direction, and here's the y direction. Okay, well, in the x direction, I know that it's going to travel. I need to split my screen here real quick, so hang on. So it's going to travel, I know, a position of x relative to velocity initial times time. Okay? Likewise, in the y direction, it's going to travel a distance of h. Well, let's do this. A good equation, if we're talking about position in time is delta y equals v initial y times time plus 1/2 gt squared. But because it's a horizontal launch, this whole term drops out, and I'm not going delta y, I'm actually moving h. So I can rewrite this equation based on the variables given to me. H equals 1/2 g times t squared. Now I need to compare them. I need to find the relationship between x and h. Okay, I have two separate equations. In order to get two separate equations, into one, I need to find a variable that they have in common. Remember, this type of motion, the X and Y direction, are simultaneous but independent, which means, these two variables are the same. Let's isolate them. X over V naught equals T over here. I'm going to just do this real quick. 2H divided by baby G equals T squared, or let's just do it real quick with my thumb. There we go. I have these two statements. We're knowing that this time and this time are equal. Why? Because these two things happen simultaneously. Let's set these two things equal together. Over here, X over V naught. Can you see that even? Sorry, Maddie. I'm not even on YouTube right now. I'm on my other screen. I'll move back over here. There we go. So here we go. We're here. X over V naught equals T. We simplified this. Square root of 2H over G equals T. So I pulled this over here. Let's pull this because they're equal, because they are simultaneous. And then we solve for X. X equals V naught times the square root 2H over G. And I believe that's what my answer key says. Now, could I have solved it in terms of H? Could I have like isolated H instead? Yeah, totally. It doesn't matter. The point was I was trying to find a relationship, an equation between X and H. That was the goal. And so that's what we ended up doing here for number 37. Tanner and Avi, does that make sense? Abby said, thank you. So I assume it does. The idea of setting two equations equal to each other and isolating a variable, we've also said derive an expression. That was, I believe, lab formative number 5. So deriving an expression, here's that process. And then the idea of simultaneous but independent, simultaneous is a lab formative 8 concept. So both of those lab formatives hopefully make a little more sense if you were still struggling to finish those. Other questions we got going on? And if you want to ask a question while I'm going through a problem, like go ahead and do it. I can catch up. Okay. Other questions? If not, I'm good. We can wrap this thing up, you know? Don't be afraid. If you have questions, fire away. Otherwise, we might end this thing without you getting your questions answered. So. Marcos is asking number 44. Let me see what number 44 is, Marcos. Where will the ball have a velocity of 0 meters per second? That's a fantastic question because guess what, Marcos? Where is that ball coming to a stop? That's the idea here, right? On an object that moves, number 44 is a projectile. It's launched at an angle like this. And the question goes, where does the object have a velocity of 0? Anywhere from A to D. And the answer is nowhere. Like the object is moving 100%. Again, this question is using words to try and confuse you. Because most of you, most physics students, not most of you, I mean most physics students like nationally, globally, right, would say that at the top, at its apex, there's a velocity of 0. And we all know that's not the case. Like use your human brain and not your physics brain. Do objects come to a stop when they are launched like this at the very top? No, right? Like no, they don't. They move consistently. So the question, Marcos, if the question asked when is the vertical velocity 0, then right at the apex. Totally right at the apex, that velocity is 0. When is the velocity 0, though, is a different question. But like rephrase it. When does the object stop moving? Like, no, it doesn't. Until it hits something, right? Until it comes to a rest, but it doesn't. And yes, unfortunately, the words and wording is a thing that we have to, push back against, because at the end of this thing, we have this AP exam. So again, if wording is confusing you on anything and any problem, I will not let physics words be the reason you get questions wrong. So in an assessment or something, ask me and I will explain the wording to you. How do you know which equation to use? I understand. 1C. Let me check what 1C is, Tanner. I assume you mean 1C here. Calculate the displacement of the runner from 0 to 8 seconds. Okay, so from 0 to 8 seconds, Tanner. So we have the area. Like, if me personally, you only have to solve it one way, or I guess they ask you to solve it both ways. Most likely on an exam, I would not ask you to solve it both ways. I would say use one or the other. So if you're a graph person, and in this case, because it's a trapezoid and I'm good with like squares and triangles because my brain's pretty simple, like I would break that thing up and do area. But in terms of the equations, we have two different types of motion there. We've got constant velocity for the first 3 seconds, I think. And then we have got constant acceleration for the last 5 seconds. I could be wrong with my timing there, but the first 4 seconds is constant velocity, and the last 4 seconds is constant acceleration. So I would have to go ahead and the key is actually a little backwards because it's written kind of like opposite. So for the horizontal line, if I'm moving at -3 meters per second for 4 seconds, I can figure out how far I've gone. -3 times 4 is -12. Got it. I know how far I went. For the last portion, when there's constant acceleration, you may want to use the equation that equates position and time. So that's our change in position equals v initial times time plus 1/8 squared. And in order to do that, we have to find the acceleration of this object. And it doesn't tell us the acceleration. Well, I guess we solved for it in part B. So we can plug that in. Do you want me to write it out on the board, Abby, or do you understand, or do my words make sense? I can take 2 seconds to write on the board if you need me to do so. Okay, yeah. So in my opinion, I would use the graph and just use the area. But if I'm for some reason required to do it, 2 different motions. Horizontal line is constant velocity. Slope line is constant acceleration. Kind of, right? Like you kind of have to. I mean, you don't have to remember those things. Yeah, I mean, it helps, but you'll get used to it. Remember, the first variable that you see in an equation is always your y variable, right? Like that's always your y variable. And then finding your x variable or your, independent variable allows you then to make your Jesus fish expression. So and they're formally called proportionality statements, just so we're all clear on that. I don't want you walking into like your math class being like, oh, we're doing Jesus fishes today. Like, no, they're proportionality statements. It's just silly when we call them Jesus fishes. What else, folks? What else? How I would solve question 3. Well, Simon, I would solve question 3. The answer key tells me how to solve question 3. Oh, I suppose it doesn't. These are motion maps. Do I want to go over the motion map with you? No, we didn't cover motion maps in class. They will not appear on your exam. And when it comes time to review for our AP exam, we may review motion maps, but otherwise cross number 3 out. We did not cover motion maps this year. All right, see you, Tanner. Have a good night. So Simon, don't worry about question 3. See you, Marcos. To the other 15 of you sitting here, if you're done, I get out of here, because I'm trying to figure out when to end this thing. And if there's 15 people of you here and you don't have questions, like, then get out of here. Like, go study, go look at your lab formatives and stuff. See you, Casey. Again, if you get questions, put them in the chat. Put them in the chat. Ooh, I just got weird. I just got a remind from a student asking me to do one. That's okay. Okay. See you, Maz. See you, Simon. Let's do number 10. Number 10. I don't know I'm not going to try and out you, but the person that sent me the remind number 10 on YouTube, I don't know what you mean. What do you want to see? There's obviously the answer key gives you the way to solve the problem. So I'm trying to figure out what question you have about number 10. If you were the student that asked about number 10 on remind, what do you want to see about number 10? Can you explain why you label the velocity graphs the way they are labeled? Can you explain why you label the velocity graphs the way they are labeled? Car starts from rest. Explain how your graph illustrates the correct answer. Well, let's get out the whiteboard then to sketch a graph. We're on problem number 10. And the question was, can you explain why the graph is labeled the way it is on the answer key? So we're going to go ahead and do that. Number 10, it gave me the axes V and T. And that's it. So then it says a car starts from rest. That's the y-intercept because it starts from rest. That's my initial velocity. Car starts from rest, accelerates at a constant rate in a straight line. So I know that there's a constant slope here. In the first second, the car covers a distance of 2 meters. So, okay, well, there's my first second. Got it. How much additional distance will the car cover during the second of its motion? Well, because I know that we can call this over here V and 2V. Because based on this graph, it's linear. I know it's linear because velocity and time when an object is accelerating are linearly related. I can say this, right? Like, this is a cool statement to make, right? Velocity is related to time. So if I go from 1 second and I travel a speed of V, when I double that time, when I double the time I've been moving for, I've doubled my speed. It's a proportionality statement. It's also like common sense kind of when it comes to acceleration, right? Like, if I'm speeding up constantly, after 1 second, I'm at a certain speed. After twice that time, I'm at double that speed because I'm constantly accelerating. So it asks me to draw a velocity and time graph for this object during the first second. Okay, then extend your graph out to the second second. Done, right? Like that's it. Bam. Okay. How much additional distance will I have to cover now? So now distance is a weird thing. I can do one of two things here. What I would like to do here is tell me anything about my motion, distance of 2 meters. The first second card, okay, got it. So distance, again, if I have a VT graph, the area of the VT graph is position, or it's really displacement. Is displacement. Which means in the first second, I travel 2 meters. The area right there is 2 meters, which is equal to the velocity times time, times 1/2 because it's a triangle. From there, you can find your velocity at V1, or at the first second. You can find your velocity after 2 seconds, and so on and so forth. So that's kind of number 10 in a nutshell, and how you might solve that problem. Shelby, you said why. Which one is why to what? Can you elaborate? I just checked over here again. I was looking at the review guide to make sure I was answering the question. Why what? Or Shelby, or did it maybe perhaps they answered your question somehow after you said why? Shelby, are you still there? Oh, okay. Okay. Because it's late on a Sunday and you're getting tired. That's why I got tired. All right, folks. That's funny. That made me laugh, Shelby. Thank you for that. Okay. We're almost to an hour. That's a long enough YouTube video, I think. If you showed up a little late, the first portion is kind of my little review session type deal. And this last session was probably 4, maybe 5 questions that I answered about the review guide. So again, the answer key is on Canvas underneath keys and videos, keys and links, something like that on Canvas. It's there. You're going to click on that. And then at the top of that list, at the very top of that list, there will be Unit 1 review guide answer key. So check that. Lab formatives are due tomorrow. I've actually already graded the lab formatives. I graded them before I came on here. And so I'm not going to look at them again until probably tomorrow morning when they're due. So these kind of like last submissions for lab formatives. Turn those in. And I will see you all either during early bird tomorrow or during 6B and 7. Get there as soon as you can, and we'll start the test right on time. Okay? 1 unit down. We're doing it. I will see you all later.